at this part. All right. When it talks about the dot product, another name for the dot product is the inner product of two vectors. All right, is this. All right, if one of the vectors is u1, u2, and the other vector has components v1, v2, then when we do the dot product, and the dot product is indicated by having that little dot in there between them, then what you do is you multiply the horizontal component here by the horizontal component there, put a plus sign, and then do the vertical component by the vertical component. All right, now the thing to note down here is that the dot product of two vectors is not a vector, it's a scalar. In other words, it's just a number. All right, now on this next page, we're going to just find the dot product. So right here, if I want to get the dot product of these, then the dot product will just be equal to the first component times the first component, and then a plus sign, and then the second component times the second component. And so we get negative 4 minus 6, which is negative 10. Now, notice that negative 10 is just a number. And numbers are called scalars. So the dot product then is a scalar. All right? Does anybody have any questions about that? It's easy to calculate. All right? And now, again, why it's going to be important is going to be because it helps us to find the angles. Now, on this one, there's some stuff that did not print too well. And so what I'm going to do is I'm going to tell you what is important about it. All right, it says let U and V and W be vectors, and it says and let C right there be a scalar. All right, the first property that vectors have is that if you do their dot product, it's commutative. In other words, if you do the dot product of U and V, that's the same as the dot product of V and U. Now, I'm just going to show you one thing about this because it turns out that this isn't the biggest thing in the world. But remember, if you've got the U1 and U2 for vector U, all right, and then you've got that the vector V is V1 and V2, all right, then if I do U dot V, then I'm putting this one in first times that one, so I'm going U1, V1, all right, and then I'm going U2, V2. Now, if I do V dot U, then I'm putting the V1 in first, so this is V1, U1, and then V2, U2. Now, the U's and the V's here are just numbers, and since multiplication is commutative, then this is the same as that, and therefore these two things are obviously so. Okay? Now, we're not going to go through every property like that, and all I want to do is I want to tell you which of the properties actually are important because we don't use a lot of these. All right, this second one here, this is one where it did not print well, but it's this. It says U dotted with itself is the same as the length of U squared. Okay? All right, remember that the length of U, this thing right here, would just be if U is U1, U2, like that, then the length of U would just be U sub 1 squared plus U sub 2 squared. All right, so that's what the length would be. Now, if I do the length squared, so that would be this with the square, then it's just going to take the top off of that and be U sub 1 squared plus U sub 2 squared. Okay, now, if we do the dot product of those, all right, we're going U sub 1 times U sub 1 plus U sub 2 times U sub 2, and so you'll see that this is U sub 1 squared plus U sub 2 squared, which is what this was. Okay, and so that just tells you that this property is true. All right, now once again, I'm going to circle this in green just so you can tell that's the property. Now, this one is relatively important to us because if we take the dot property with it, the dot product of something with itself, then we don't get a square root in the answer. We just get the components squared. In other words, we get the gut part of that right there. Okay, now in this one, All it's saying is that if I have the 0 vector and I dot it with any other vector, I get the scalar 0. Okay? So now, what that is this. The 0 vector is this, all right? And then if I take some other vector, so if it's just u, we'll call it u1 and u2, like that. And if I dot those, then I'm going to get 0 times u1 plus 0 times u2. And these two zeros now are just scalars. And 0 times any number is 0. 0 times the number is 0. So we just get the scalar 0 there. So technically that's true. We're not going to use that a bunch, but it's true. All right. Now, this part right here is nothing but a commutative property. Okay? And so you just want to remember it as that. I'm sorry, I said commutative. I meant distributive. It's just like the distributive property. And this one is called a left-hand distributive property. In other words, if you're going to dot this vector with the sum of two vectors, then it's the same as dotting u with the first vector, dotting u with the second vector, and adding them. So it looks just like distributive property. And this one, the parentheses is supposed to be here and here. So it's supposed to be u plus v times w is equal to uw plus vw. All right. Notice that the number that's getting distributed this time, not the number, the vector that's getting, in essence, distributed is the one that's out here. So this is called a right-hand distributive property, where the one over here is called a left-hand distributive property. All right. Now, on things that are not generally commutative, that's a big deal. Here, it's not going to be such a big deal. Okay, and then right here, all that this one is saying is if I have a constant times some vector u and I dot that with v, then I would get the same answer as if I took the u and then I put the constant over on the v and did the dot product, or it would be the same as if I did the dot product and then multiplied by the c at the end. They're saying all of those will give the same answer. Okay, now, out of the ones on this, the one that's the most important is this one. Okay, now, we're going to look at this thing about the angle between two vectors. All right, it says if theta is the angle between the non-zero vectors u and v, then the cosine of theta is equal to the dot product of the two vectors divided by the product of the lengths of the two vectors. That's what this is saying here. And so theta then is going to be the cosine inverse of the dot product over the magnitude of u times the magnitude of v. Okay, now the proof for this happens to be at the top of page 516 in the book. You can look there. I used to go over this proof and no one followed it. So I stopped going over it. But if you want to look at it in the book, it's an example of the law of cosines applied to vectors, and it makes use of these properties that were back on this page. Okay? All right. Now, this is a fairly widely used formula, and if you're really interested in what it says on page 516, if you want to look there and try to follow it and you have trouble following it, if you want to come by someday, like during my planning period or after school, I'll sit down with you. We can go through that. But it's one of those things that it's because we don't know a bunch about vectors. It's sort of complicated math to get it. But all it is, if you remember, it's just the law of cosines, and then it works out to give you this thing here. Okay, now this you will need to memorize for the test. I don't know if you want to learn the part on the left or the part on the right, but we're going to practice this thing about getting the angle between two vectors a bunch. All right, now on this one it says find the angle between the vectors u, which is 3, 2, and v, which is 1, 0. All right, now a visual is always a good idea for these. So if we have the vector 3, 2, then that's this vector. And then if we have the vector 1, 0, that's this vector. All right, now one is I think you can tell that there is an angle here, and that's the theta that occurs in the formula. Okay, now to find that angle, we have to do three things and then put it together. The first thing we need to do is we need to find the dot product. Okay, so in this case, we're just going to go 3 times 1 plus 2 times 0, which will give us 3. Now, because this is being recorded, I'm just going ahead, instead of asking a lot of questions and telling you stuff, until it gets to the time when I think, okay, I might be losing you, and so I want you to ask questions. But if you want to ask a question, just raise your hand. I'll acknowledge you. I'll just have to repeat the question. All right. Now, we need, this is the first thing we need to find because it's the top part of that formula back on the other page. All right. The next thing we need to find is we need to find the magnitude of the first vector. All right. So here, the magnitude of this is just going to be 3 squared plus 2 squared. And so this will be the square root of 13. Then we have to find the magnitude of this vector. All right, and so that's going to be 1 squared plus 0 squared, and that's going to be just the number 1. Okay, now if we plug all of this into the formula, we get the cosine of theta is equal to the dot product, the u dot v on top, and then we get the square root of 13 times 1 here. All right, so now theta then just becomes the cosine inverse of, and this simplifies to 3 over the square root of 13. All right, would you take your calculator out? And we need to talk about how we're going to get the calculator to do this. All right, in your calculator, you need to go to mode. All right, and make sure that you're in degree mode here because we will want the angle between the vectors to be in degrees. So you'll go to degree mode. Then once you've done that, we will just go second cosine and then 3 divided by the square root of 13. Now, in this case, we're real fortunate because one vector has a length of 1. We'll do another one of these in a minute to show you about what happens when it doesn't have a length like that. So here we got 13 like that. Now, we're going to get out of that and put the parentheses and then press enter. And so our angle here, we will give answers to this to the nearest tenth of a degree usually. So we would get here theta is equal to 36.7 degrees. All right, so theta equals 33.7 degrees. Okay, now let me put this down for a second. Does anybody have a question about just that one problem? Okay, because we're going to practice with a couple of these, though I think you'll find it's easy. Now, one of the reasons that we're doing this is in physics, there are certain things that you have to do. And if you've got two forces working in different directions, sometimes you just need to know the angle between the forces. Okay? And so we can calculate that using this. All right, now look at this one. First of all, when you look at this problem, I think you can just see the angle is going to be bigger than 90. All right, now there's going to be something that happens in the formula when the angle's bigger than 90, and I want to see if you can pick it out. All right, now let's just do the work. We're going to find u dot v. Okay, so we're going 6 times -7 plus 1 times 2. All right, and so that's going to be -42 plus 2, which will be -40. All right, and then when we get the magnitude of u, we're going to be going 6 squared plus 1 squared under the radical, and we're going to get this square root of 37. All right, and then when we get the magnitude of v, all right, we're going to get the square root of -7 squared plus 2 squared. So that's going to be 49 plus 4, which will be the square root of 53. Okay. Any questions in just calculating those just little things? Okay, so now to get theta, remember theta is going to be the cosine inverse, and then the dot product goes on top, and then these two things go on the bottom. All right, so square root of 37 times square root of 53. Now, when we're putting this in a calculator, I want you to remember a property from Algebra 2. Remember how the square root of a times the square root of b is equal to the square root of A times B. It's easier to type this into the calculator on the bottom there as being the square root of 37 times 53 rather than put two square root signs. Because if you put them as separate square root signs, unless you put a parenthesis around them, like I'm doing right here, then the calculator is going to take that as negative 40 divided by the square root of 37, get that number, then multiply by the square root of 53, and quite often you'll get an error message because you're going to get a value bigger than, in absolute value than 1, and so you couldn't take the inverse cosine of it. So it is important to enter it this way to keep from making that mistake. All right, now let's calculate the angle. All right, so we want the second cosine. All right, we had negative 40, and then we're going divided by, and we're going second square root, and we need 37 times 53, like that. All right, right arrow, and then a parenthesis, and it should give us the angle. And so we get there that theta is 154.6 degrees. So, okay, now let me ask you a question. Is there a sign that we could have here that would say, I know the angle is going to be bigger than 90 now? Or if it wasn't this way, we would know the angle was between 0 and 90. There's something here that told us it was going to be bigger than 90. Any ideas? Mike?
Is it that vector B is bigger than vector U?
All right, in magnitude?
Yeah.
Okay, I'm going to say the answer to that's no, because if we had both of them going in this direction, it wouldn't matter which one's longer, the angle could still be less than 90. Okay, so, I mean, that's a good guess, but it's not what happens here.
Is it because one of the x-coordinates is positive and the other one's negative?
Okay, in other words, you're talking about this thing being negative here.
And the other one being positive?
Okay, all right, now, I'm going to say it's related to that, but it's not that directly.
Is it because the inverse cosine is negative?
All right, okay, it is because the inverse cosine is negative. All right, now, look at this thing right here for a minute. Do you see that the part of that makes this negative is the dot product being negative right there? Okay, because the square root is going to turn out to be positive, right? Okay, so anytime that we do the dot product and we get a negative value, it's going to make that cosine inverse negative. And remember that on the cosine inverse, when we were doing the unit circle, when we were thinking about cosine inverse, we were over here in the first and the second quadrants. And over in the second quadrants, remember that's when all those cosine values were negative. Okay, and so that is the thing that makes that happen. All right, so basically if your dot product is positive, you're going to get an angle less than 9. Okay, now let me put this down for a second. And I want to ask you, before I go to this one, I want to ask you a question here. Consider this for a minute. Suppose I had a vector like this. Let's just call this 5, 2 for a minute. And then I had a vector that's down here like this. And let's say this is 5, negative 6 right here. All right. Do you see that when we get the angle between the two vectors here, it's going to give me that smaller angle that's less than 180 every time? In other words, just because this one's in the first quadrant and the one down here is in the fourth quadrant doesn't mean that it's going to get that value right there. Okay? It's always going to get that angle that's, in other words, for us, theta is going to be between 0 and 180 degrees every time in this form. Okay, that's what's important in that. Okay, now, here we have an interesting phrase that's called orthogonal vectors. All right, Does anyone know the meaning of the word orthogonal? Okay. I don't know what you're reminded of when you hear a term like that. Is it something like Ortho Carolina? You know, you just ortho meaning more like somebody that does something with bone or muscle stuff. All right. Orthogonal is going to have virtually the same meaning as forms a right angle. Okay? All right? Now, the only time it won't have exactly that meaning is if one of the vectors is the zero vector. Okay? So now, consider this for a minute. It says two vectors u and v are orthogonal, all right, if and only if is the phrase here. Because again, it misplaced some print there. If the dot product is zero. Okay, now let's go to this next slide, and I've got a couple here. Look at these two vectors here, and we want to see if they're orthogonal. So we're going to go v dot u, and it would be okay if we went u dot v. It doesn't matter the direction in which we go here. So we're going to get -3 times 8 plus 4 times 6. And so we get -24 plus 24, which is 0. All right. Now, because that's 0, it tells me if I do this on graph paper, that angle should be a right angle. Because remember, the cosine at 90 degrees is 0. And so that's what's got to be happening here. All right. Now, let me demonstrate that with just a graph here for a minute. All right, if we graph the vector -3, 4, all right, it goes like that. All right, now I don't have it drawn perfectly straight, but it's close enough you get the picture. All right, now if we do 8, 6, this is 8, 1, 2, 3, 4, 5, 6, that's here. Okay, so now if I come straight up to there, then what they're saying is that angle is going to be a right angle. Okay, now the good news about this is anything that gets used in physics, usually it makes some kind of practical sense. You know, sometimes math can be sort of theoretical. You know, like when we have imaginary numbers and stuff like that, you probably don't know a real use for imaginary numbers, though there are some. Okay, all right, but you probably don't know a real use for that. But in stuff that's related to physics, generally speaking, most of that's got some kind of practical bent to it. All right, so anyway, this is orthogonal. Okay, now I want you to look at the second one. All right, when it says, what about 6, -1, and then the vector k that's 0, 0. All right, so if we do w dot k, then you can tell we're going to get 6 times 0 plus -1 times 0, and everybody knows that's going to be 0. All right, now, technically, these two vectors are orthogonal. Now, what I want you to do is I want you to look at the drawing for this one. All right, if we do 6, -1, that's this vector. All right. Now, in blue, I'm going to do the vector 0, 0. All right. Do you see that that one is the one that's just a point instead of having length to it? All right. Now, do they make right angles? All right, they don't. In other words, if it's just a point, you can't declare that there's an angle there. All right. And so this is the only reason why when we talk about the vectors being orthogonal, that we use the term orthogonal. Because unless one of the two vectors is the vector 0, 0, and that's the reason that you get the answer of 0, then the two vectors have to be at right angles. But in this case, that blue dot is not making any kind of angle with the green vector, and so we use the word orthogonal to cover that special case. Anybody with a question about those? Yes, ma'am.
So the second one is orthogonal?
Yes, well, both of them are orthogonal. The first one, though, makes a right angle. And the general meaning of orthogonal means the two vectors are at right angles. But this one case that I've got drawn right here is the exception case. In other words, one of the vectors is 0, 0, hence there is no angle. Okay, and so we just, but we still refer to that as being orthogonal. But in this case, though they're orthogonal, they're not making the right angle. The rest of the time, for them to be orthogonal, we really do have vectors, and the angle is 9. All right, so that's the significance of that. Okay, now, this next part right here is the most interesting thing that we do with these. And I'm not great in physics. I know a little bit about physics, but I am not great in physics. But in physics, a lot of times you're going to project one vector onto another vector. All right, I'm going to make a drawing down here. A lot of times when we think about projecting a vector, if this is the vector that we start with, a lot of times we'll project down to the x-axis. And so all we do is we drop a perpendicular from this endpoint down to wherever we're going to do the projection. All right. And so in this case, the part that I've got right here, that's just the x component. The length of that would be the x component of that vector. But that would be the projection. All right. Now, suppose that I want to take a vector and project it onto another vector, but the other vector is not horizontal. All right, so that would be like in the case that we're looking at here. If we take the vector u and then we're going to project it onto this red vector, then we're going to drop the perpendicular that's coming right here. All right, and this vector right here is going to be called the projection of u onto v. And that's where that symbol comes.
So which is the orange vector? Red one?
All right, the one I just referred to as red is what I called orange up there. All right, because technically I don't think that's exactly red, but it looks pretty red to me. Okay, now, before we get into this, I want to just tell you a couple of facts because it might hit off some questions. All right, the vector that's the projection can be smaller in length than the given vector. It usually is, as a matter of fact. But compare it to the vector v that we're projecting it onto. All right? In this case, the projection is less than v. All right? I want to make another drawing here, though. All right? Suppose that this was vector u, and then let's suppose that right here, this vector is vector v. Okay, now, if I do the projection this time, I've got to start right here, and I've got to drop a perpendicular down to where it would meet this. Now, it's sort of like the old altitude in an obtuse triangle. We talk about it being perpendicular to the line containing the opposite side. Okay, now, if I go out there and make that right angle, then this vector that I'm going to draw in red right here is the projection of u onto v. So this time, do you see that the projection is longer than the vector it's getting projected onto? That can happen. Okay? Now, I think what happens more commonly is the thing that's depicted in this drawing, where the projection is somewhat less than the original vector. All right? But anyway, you just need to know that when we project it, we just drop a perpendicular from the end of a vector down to the vector we're projecting it on, and then whatever from the origin out to that point where that perpendicular drops there, this thing is called the projection of u onto v. Okay? Now, have y'all done anything like that in a physics class? Okay? Now, let me ask you this. I'm just going to throw this in as just a thing. All right? Have y'all had like an object sliding down an incline? Okay, now if you have that object sliding down the incline, then don't you do something like this. You take the thing that's going down to the center of the earth, and then you take the thing that's in the plane of this, and then you take, let's see, I just did that wrong. Just a minute, let me think. All right. Let's see. you get one that's going perpendicular here, you get one that's going there, and then you get the one that's going down towards the center of the earth. All right, don't you know a diagram that's like that? Okay, and so like, let's say this had a weight or a mass of 10 kilograms, then a certain amount of that mass would be pushing down here. But if this was like on something that was like ice, like we've had recently, then this thing could be sliding down this way, and so there would be a certain amount of the force that's going down this way. There'd be a certain amount of force going this way, and then this one right here, wouldn't it have the magnitude of whatever that weight is, the 10 kilo, or the mass is, the 10 kilograms?
I wouldn't be the force of gravity.
Okay, but isn't that, but it's the force of gravity, but doesn't the force of gravity acting on something give you its weight basically, or it's affected by its mass, right?
It would be the mass times gravity.
Okay, so, but anyway, so this one is related to the mass that's here, okay? Now, but what happens here, if I take this and I project it down to this one, that's at right angles to this inclined plane right here. So if I project it this way, then this thing this thing, it's this part right here is the projection of its mass down towards the center there. So it tells you how much of that weight is actually going down into the incline. All right, so this thing right here would be the projection right there. Okay, so that's what it's talking about. All right, now I'm not good enough at the other stuff to just tell you a bunch about it, the same way that a physics teacher would do. But I do know, we can find out what this angle is, so we can get the incline, and then we can get all the math stuff to work out for that. Okay, now let's go back to this for a minute. I just want to read it so we make sure we got it. This is when given a vector u, so that's this vector right here, all right, and a vector v, that's the purple-looking vector here. All right, then the projection of u onto v is the vector, that's this one right here. That's formed by dropping a perpendicular from the tip of u to the vector v. All right, in the diagram, the orange vector right there is the projection of u onto v, and is denoted by the symbol. The projection of u onto v is how this is read. Okay, now, there is a formula that we get for this thing. All right, and this formula is related to the angle between the vectors formula. Okay, so now it says this: if u and v are non-zero vectors, then the projection of u onto v, which is given by this symbol right here, it's this. It's u dot v over the magnitude of v squared times the vector v. Okay, now this thing right here almost looks like that formula for the angle between the two vectors, except it's v times v instead of being u times v. Is what it looks like. Okay, now this quantity right here is a scalar, and so what we're going to do is we're going to take a scalar and multiply it by v. All right, now if this scalar is less than 1, the projection will be less than the length of v. If the scalar is bigger than 1, the projection will be longer than v. All right, now on this next page, I have got the proof of this thing. All right, so let me see if I can go through this with you in a way that makes sense. All right. All right, right here is the vector v, okay? All right, here's the angle theta, and then we drop the perpendicular right there, okay? So now, we know all of the following because this is a right triangle right here. Then if I do the cosine of theta, the cosine of theta is going to be equal to, let me call this thing right here x for just a second, it's going to be x over the magnitude of u right there. And so now if I cross multiply here, I get x is the magnitude of u times the cosine of theta. All right, and so that's how I got this expression right here. Now, in a similar fashion, I did the sine of theta is equal to, I'll call this y for a second, is y over the magnitude of u. And then when we cross multiply here, we get y is the magnitude of u times the sine of theta. Okay, so now for what that's worth, this is true. Okay, now, do you remember this expression right here? That expression right there is a vector that is 1 unit long that's going in the direction of v. Now, when we've seen it before, instead of calling it v and instead of these, we had this. We had it with u's, but remember, this was defined to be a unit vector in the direction of v. Okay, so now, if this is a unit vector in the direction of v, then the projection, let me erase what I've got written right here for a minute. So we're back to here. Then the projection, which is this thing right here, all right, it should be then this length times that unit vector. Okay, and so we have this part right here. All right, now, remember that the angle between the vectors, the cosine of theta, was the dot product over the length of u times the length of v. Okay, so what we're going to do is we're going to put this junk where that was, and it gives us this statement right here. So there's our magnitude of u, and then in place of the cosine, we got all this garbage, and this is our v, this is our unit vector in the direction of v. Okay, so now, if we look at this, this is going to cancel that. And so what we have left then is we've got the dot product of u and v on the top. We've got these two things multiplied by each other, which would be this on the bottom. And then this is the vector v right there. And so that's how they got that formula.
I use the restroom.
You may. All right, now, you will not be held responsible for trying to derive the formula, but you'll be held responsible for memorizing it and using it. So you will need to know this thing right here. Okay? All right, now, we're going to make use of that here. All right, now, before we start doing this problem, I want to tell you something about it. We're going to get this nice, great looking answer to this problem, all right, because when the teacher teaches you something, they don't want you to, just swallow hard doing the math till you get the concept. So this first problem is just, we're going to do easy math so we can apply the concept. Now, once we get done with this one, most of the problems that you're going to actually see with this in the homework, instead of them coming out with whole numbered values in these two places right here, you're usually going to have fractions. And some of the time, it's going to be ugly looking fractions like a 181 over 97, junk like that. All right, because this has to work no matter what the vector is. And so most of the time, you get something that's a little bit strange. All right, now, this problem is actually going to have two things to it. The first thing that we're going to do is we're actually going to find the projection, and then we're going to talk about the relationship that the projection has with the original vector. All right, so that's the two different things. Okay, so now, in number one here, where it says, find the projection of the vector u, where it's u is 6, 2, onto v, where v is 5, -5. I want to draw that here, and I would suggest that you draw it on yours. So that's where 6, 2 is. So we're going to draw that, and we're going to refer to this as u. All right, and then we're going to do 5, -5. All right, and this is vector v here. Okay, now, physically, I'm going to try to draw in the perpendicular here. So I'm going to be coming in this direction. Okay, now, if I have got that drawn right, then this little part that I'm going to draw in blue right here is what we should get for that projection. Okay, and now the math is just going to make it come out like that. All right, so let's look at this. So when we get the projection of U onto V here, remember it's the dot product of U and V. So if we do U dot V like that, then we're going to get 6 times 5 plus 2 times negative 5. All right, so this is 30 minus 10, which is 20. Okay, so we're going to get a 20 up on top here. All right, now the next thing we have to do is we have to get the magnitude of V. Okay, so when we get the magnitude of V, all right, this is going to be 5 squared plus negative 5 squared, all right, which is going to wind up being the square root of 50. Now, we could simplify that, but remember that in the formula, we want the magnitude of V squared, okay? And so instead of simplifying it, if we just leave it like it is, then when we square it, it's just going to take the top off of it, and so we're going to get the 50 right there, okay? And now we're supposed to put right here the vector V, which is the 5, negative 5, okay? Now, this part right here, this just becomes 2/5, and then if we scalar multiply here, then 2/5 times 5 is 2, and 2/5 times negative 5 is negative 2. And so notice that we get this nice, beautiful, integer valued answer. Okay? Now, if you look at this thing in blue here, there's 1, negative 1, here's 2, negative 2. All right? And so it agrees with that. In other words, our diagram agrees with it. Now, we had something going for ourselves here that you need to look at. All right? Do you see that I put something in here that had a slope of negative 1? All right? And because that had a slope of negative 1, then when I'm going to do this perpendicular, it's going to have a slope of positive 1. So I got something pretty easy to deal with here. And so it was nice to be able to make that. Okay. Now, Julie, you had a question.
Oh, never mind. I understand it now. I thought it was a different.
Okay. All right. Now, everybody, if you look at number 2 where it says make a graph showing U, V, and the projection of U on the axis, all right, that's what we have already right here. Okay. Now, right here in number 3, all right, now you understand that I've been making out new tests this year. All right, but there will be a problem like this on the test because it's one of the concepts that we're supposed to do. All right, and so this is one of the problems that people tend to miss, though they think it's easy. So you either get it right because you remembered it, or you never understood what it was talking about, and therefore you don't know where to look. But it says right here, write U as the sum of 2 orthogonal vectors, one of which is the projection. Okay, now, so remember that U is this one right here. And then it says the sum of 2 orthogonal vectors. Remember, orthogonal just means vectors that make a right angle. So do you see that the blue vector right here and the black vector right there are the 2 orthogonal vectors? Okay, now, let me erase what I've got down here for a second. And so if all you have to do here is be a translator. So it says write U as the sum of 2 orthogonal vectors, one of which is the projection of U onto V. And then right here, I'm just going to write this other thing like that. And our deal is we got to come up with this. Okay, so now right here, remember that this was the vector 6, 2. Okay, now the projection that we got was 2, negative 2. And now what we got to think of is what goes in these 2 places right here to make that statement true. All right, what would we need to add to this 2 right here to get this 6? All right, 4. all right? And what would we need to add to this -2 to get 2 here? All right, 4 again, okay? And so writing this statement is this number 3 part. Now, that looks easy as crap because these are integers, all right? Now, let me get you to practice something here. Suppose we had this, all right? Suppose that I had the vector was 6, -2, all right? And let's say that our projection turned out to be 15/4, -2/3. Okay, now, again, we're just assuming it did that. All right, so now the question is, what do I get here? So I'm going to just put an A and a B there. Okay, so do you see that for us to get this right, all we're going to do is we're going to take the first thing here, the first thing here, the first thing there. So 6 equals 15/4 plus A. All right, so you can solve this a couple of different ways. Algebraically, if you want to just multiply by 4, you could get 24 equals 15 plus 4A. And so here we'd get 9 equals 4A. A is equal to 9/4. Now, you can write that as 2.25 if you want to, but 9/4 here would be a nice simple answer. And then you could do a similar thing, go -2 equals -2/3 plus B. And we could do the same kind of work to get what B is. So when you have fractions, now notice I made a nice fractions there. We didn't have anything with 2-digit denominators and 3-digit numerators, which you'll have some in the homework. All right, but all you do is you just do it like this, and then you do whatever the math takes to get that in. And so here, just so we'll have completeness, I'll write what this is. We'd multiply by 3. Now I'd add 2 and get -4 equals 3B. And so B would be equal to -4/3. All right, and so that vector right there would be the thing we're looking for then. Okay, now, the one thing I want to tell you, because somebody's going to take this more literally than I meant it. All right, these two things right here are not at right angles to each other because this is not the projection of that onto, well, it might be the projection of that onto some vector, but it's not a normal problem. Okay, now, tonight's assignment is to do this part. The part that I have right up here, this was in the last assignment, and so you don't have to redo that. All right.
Will we be able to see our test?
Yes, I'll go ahead and give this back to you. All right, so let me stop the recording here.